So we're looking at Unit P, page 2. We'll take a look at numbers 3 and 4 here. So number 3 is going to be a parabola because we only have one of the variables raised to the second power. So it would not be an ellipse or a hyperbola. So it's always a good idea to have in mind, what you're up against. All right, so I'm going to reorganize and rewrite it. Y squared plus 6y. I'll leave a little space to complete the square, minus 4x. Now, for the x terms, there is no square to complete. So I'm just going to write the negative 4x equals 0. Apologies. Equals negative 25 because I would vacate that 25 and shoot it on over to the other side of the equation. All right, so I'm going to use my handy dandy b squared over 4a. This is a step that most of you, if not all of you, should be able to do in your head, which is to take the b value, square it, and divide by the 4 times the a value, which is going to give you a 9. So I'm going to add the 9 to complete the square here. Because I added it to one side of the equation, I must add it to the other side. On the left-hand side, it factors to y plus 3, the quantity squared, minus 4x. On the right, it's going to be negative 16. All right. So now what I want to do is I want to get it into the appropriate standard form for a parabola. I'm going to steal a little bit of work from the next page. Not really work, it's just notes. All right, so I got all this stuff right here. If it ain't broke, you know what I'm saying? Copy. And if at this point I haven't sold you on the benefits of digital inking, I don't know that I ever will, but just the ability to copy, paste, resize, reorganize, and all that stuff, there's definitely a benefit to it. All right. So I'm looking at some type of equation here. I've already said that it's a parabola, but if you go into it kind of cold and not really, really thinking about what kind of function it might be, you could consider taking your original equation and putting it into Desmos. If my Desmos calculator wants to work, I'm going to refresh. Y squared minus 4x plus 6y plus 25 equals big old goose egg. And you see it's a sideways parabola. All right, so it gives you a little bit of a sense of what you're up against. And it'll also help you graph it if you need to. And there's ways that you can come up with your solution just from the graph. All right, so you wouldn't have to do all this work, but you want to get familiar and kind of reconnect with the ideas of completing the square and all those algebraic skills from way back when, because they're going to come up in this course over and over again. All right. Bottom line is, it's easier, if we look at what I have here, it's going to be easier to solve for x in terms of y than it would be to solve for y in terms of x, which kind of goes hand in hand with what you see on the screen. In terms of the graph, it's a sideways parabola. So that looks like the inverse of some parabola that would be in the form of y equals. All right, so I'm going to solve this for x, and to do so, well, I'm gonna get a little cute here. I'm just gonna do a little switcherooski on these two bad boys. And you can't just swap them. You algebraically swap them. So it's gonna be y plus 3, the quantity squared, plus 16 equals 4x. All right, I want to get x alone, so I'll multiply both sides by 1/4. All right, so I'm going to put a little bracket here, and I'll just write times 1/4. It's the same as multiplying by, it's the same as dividing by 4, but this makes it a little bit nicer because I can distribute it through and make it 1/4 y plus 3, the quantity squared plus 4 is equal to x. All right, so from here I can pull out my vertex. Vertex is the h and k value, so h comma k. All right, based off the model, we're looking at my k value is contained within the parentheses. My h value is beyond the parentheses. So we're looking at 4 comma negative 3. So you kind of look at it and say, well, I need a positive 3. What did k have to be in order for y minus k to become y plus 3? What a lot of people will do, just to kind of have a more mechanical approach, is they'll just say, all right, negative k has to be equal to positive 3. Solve for k. That's fine too. All right, our 1 unit slope, I'll talk about that in a minute, is the a value, which in this case is 1/4. A quarter. All right, so I'm going to draw my axes. I have to turn the volume down on the background music, otherwise I'm going to get blocked from uploading this onto YouTube. So plot the 4, negative 3. Now, normally the relationship would be for each unit away from the vertex, in this case up or down, you would increase. Normally if it's an ordinary parabola, you go up or down. Here we're going left or right. But you'd increase by 1 unit, then 4 units, then 9 units. All right? So that would be the relationship 1, 4, 9. But what the a value does, that 1 unit slope, is it acts as a scalar multiplier for each of these values. So instead of 1, 4, and 9, instead of increasing by 1, 4, and 9, I'm going to increase by 1/4, 1, and 9/4. All right, so I'm multiplying each of these values by the 1/4. Now you might say, well, I'll never need to do that because I'll use my Desmos calculator, my graphing calculator. And I say, yeah, true. But I also follow that up with, yeah, but don't you want to know? Isn't it cool to know? Let's at least try to know. All right, so 1/4 of a unit. Again, we're going to the right here because it's a sideways parabola rather than up. If it helps, just turn your head to the right so that the x-axis becomes the vertical axis, and just pretend you're plotting an ordinary parabola. All right. As I go out 2 units, so this is 1 unit out. If I go 2 units out, I'm going up 1. If I go 3 units out, I'm going up 9/4, which is 2 1/4. So 1, 2. A little bit of estimation is required. But then after that, you can just estimate it. Just do a little ballparking. All right. Very important whenever you create a graph. If there are intercepts, you have to show the intercepts. So if there's an x-intercept or a y-intercept, that needs to be part of your graph. If there's a turning point, any and all turning points need to be part of your graph. All right. But aside from that, I'm not overly concerned about things like labels or anything of the like. And also a policy that I have that's different from, I don't want to say every other teacher, but many, many other teachers, is I actually accept the Desmos graph as sufficient work for producing a graph, because this is Calc 3, so the whole point is not for me to nitpick over your ability to draw a graph, it's to nitpick over the Calc 3 content. All right, so if a question asks you to create a graph, you can create the graph using technology and submit that. All right, that's perfectly fine by me. I always wished, for years, that there was some export function on the old TI-84 calculators that would allow you to take what was on your screen and just submit that to the teacher. Because most of the time, people are just writing down what they put into their calculators anyway. Right? And I know that there are some teachers that don't even allow calculators for this course. I have a very calculator-friendly approach to things, right? Because there's enough ways to demonstrate your content knowledge in this course without having to, you know, show every single tiny little detail. All right. So the next one, like, you know, in the same vein of using technology, type in your original function. So type in, well, fun fact about me, one of the most overused words in my vocabulary would be function. It's just a habit. And so, so I'll say function even when something isn't a function, but then I'll almost always correct myself, but sometimes I'll miss it. All right, this is not a function. It fails the vertical line test, but we're actually going to learn how we can change the coordinate system to take something that's not a function in rectangular coordinates and make it a function. All right, so what I'm going to do here, again, just going into the problem, I know I'm looking at a hyperbola, and so I'm looking for the standard form, is I'm going to reorganize things and simplify and, you know, complete the square and all that good stuff. I'm going to vacate that 9. I might be the only person that calls it that, vacating. When I say something is being vacated, it means that it's being moved from one side of the equation to the other by ordinary algebraic means. So we're going to complete the square. And again, it's up to you. If you want to use the little shortcut formula, that's fine. B squared over 4a. So 64 over 16 is going to be 4. Plus, you know, positive 4. So add the 4. And then 6 squared, so b squared over 4a. So 6 squared is 36 over 4. Now the a value here, you got to be really careful. Very easy to lose sight of this. That negative 1 is the coefficient. That's the a value. So over negative 4. So it's going to be a minus 9. So on the right-hand side, I'm going to add 4, and I'm going to subtract a 9. All right. So GCFs abound. And if not, we factor a trinomial, right? Whatever the trinomial is. It should be a perfect square trinomial. But if there is a GCF, you must pull it out. Otherwise, you won't get it into the appropriate standard form. So I'm going to yank out the 4 here. That's going to give me an x squared minus 2x plus 1. I do enjoy the symmetry between courses because I'm actually in one of my high school classes, the algebra classes, I'm teaching this skill for the very first time to the students, and so here we're seeing the fruition of all those years of work. All right, so factor out a negative 1, y squared minus 6y plus 9. Right hand side, we're looking at a 4. All right. Now we're looking at perfect square trinomials. Now let's say you didn't recognize that the GCF was a negative 1 for the y terms. You would have gotten a trinomial that wasn't a perfect square. So then you'd realize, okay, well, I pulled out a GCF, but maybe it wasn't the best possible choice. All right. So maybe I pulled out a CF, but not a GCF. So x minus 1 squared minus 1 times y minus 3 squared equals 4. All right. Now, a hyperbola function. I told you, overused word. And again, I will show you how we can change variables so it will be a function. All right. So, hyperbola or hyperbolic equations, conic sections. There is a form that involves an a, but that's not the one I was going for. X minus h squared over a squared minus y minus k squared over b squared is equal to 1. But because there's a minus in here, it's not like an ellipse where you can just swap the order and everything's hunky-dory. If you do swap the order, you get a different equation, right? And a different equation would have a different different graph, right? So these are not the same. Not equivalent. All right. So we got to be careful about that. Otherwise, we pay a hefty price. All right. So what do we do? Good question. We know we got to get it equal to 1. So divide everything by 4. So in this case, it's actually pretty easy. But what I'll do is I'll show all the little details. I mean, this is a review video after all. I don't want to cut corners, especially if you're taking the time on your own time to watch this. I mean, you're doing your part. The least I can do is my part. So x minus 1 squared over 1 minus y minus 3 squared over 4 is equal to a 1. All right. So then, yeah, we did all this work. Now we got to do something with this. And not the least of which is actually getting this on a graph. And you look at it and say, well, okay, well, we got some points here. That's all wonderful, but how are we going to get this on a graph? We don't actually have to plot every single point. We just have to plot the important points. And it's going to look an awful lot like an ellipse at first in terms of the points that we're plotting, but then we're going to deviate from it in a big way. All right, the center is the h and k value. All right, so in this case, it's going to be 1 and 3. All right, so that's similar to an ellipse. All right, so that part is fine. We're going to have a horizontal and vertical change based off of the a and the b values, all right, related to the denominators. All right, so we can start our graph here based off of what we have on the Desmos display. We're looking at something that's fairly symmetrical. So let me plot the 1, 3. My horizontal change is 1 unit in each direction. My vertical change is 2 units in each direction. All right, now if this were an ellipse, so if there was a plus sign in between the two, what I would do is draw a nice little oval around it and call it a day. All right, but what we're going to do here is create an asymptote rectangle. I use that approach. There's other approaches. The one that I like is the asymptote rectangle approach. All right, so we need to create a rectangle that would have as the midpoint of each side the 4 vertices that we just determined. All right. I'm going to go with a little highlighter just to really kind of get it across here. I'll go a nice blue highlighter. The diagonals of this rectangle will be the asymptotes for this hyperbola. All right. Still should be dashed though. Now when I draw a dashed line segment or line, I always draw it with this app. I have to draw it solid first and then make it dashed after. So you just got to kind of be a little patient. But yeah, there's going to be some movement. You're going to be like, that's not a dashed line. And I say, I wholeheartedly agree with you. There's nothing dashed about either of these things. But let the magic happen. You know, remember back in the day when you were supposed to make a dashed line and you forgot? So you made it solid and you're like, okay, well, let me just erase some parts of it and everything's fine. That's all I'm doing. Of course, if you're anything like me, you did those problems in pen, and you're like, oh crap, I guess I gotta start the whole thing over again. Those were the days, right? We don't miss those days. All right. Well, maybe you miss the content. You just don't miss losing points for a solid line versus a dashed line. All right, so I'm going to need a couple of things. I'm going to need the foci. There's a similar formula that I like that's related to the method that I use for the ellipse, but we'll get to that in a second. We also need the equation of these asymptotes, the equations. So first things first, though, let's get the hyperbola graphed. It's going to go through each of these vertices. And in terms of how I knew it opened outwards rather than upwards, the hyperbola equations where the x comes first opens outwards. The hyperbola equations where the y comes first opens upwards downwards. All right. And what some students in the past have said is like, well, if you put them together, kind of looks like an x. All right. And the x comes first. They use that as a mnemonic. All right. That was kind of like more of a pre-calc mnemonic, because in that course you might have needed to know that information. Here it's like, well, how do I know it opens outwards? The other method. You type it into Desmos and look at the picture. You know, we want to also be efficient about things. You know, if you're ever in doubt, if you're ever thinking to yourself, am I showing too much work for this? Just remind yourself what the title of the course is. And then ask yourself, what are you showing on paper? Are you showing work that is specific to the title of the course? Or are you showing stuff that is specific to, you know, some other course that you took in the past? Like if you're getting bogged down in algebra, well, it's not an algebra course. If you're getting bogged down in pre-calculus, it's not a pre-calculus course. All right, I'm showing you this stuff to refresh your memories on how to go about doing this and what the underlying structures are. But if you just need to get a quick look at what an ellipse would be, an ellipse equation or hyperbola, put it in Desmos and call it a day. All right. But this is for deeper understanding. This is for the folks that haven't seen it in a while and are just like, an ellipse, hyperbola, I know those are things, I just don't know what those things are. All right. So we need the foci. What I use, and there's a similar justification, we'll save it for a different, it's a different story for a different day. But distance from center to focus is going to be equal to the difference, sum of the two denominators under the radical. All right, so the sum of a squared plus b squared. All right, for an ellipse, it was the square root of the difference, the absolute difference between those two denominators. All right, so in this case, it's 1 plus 4, so root 5. The foci are always on what's known as the transverse axis. So the transverse axis is the axis, the imaginary line segment that connects the vertices that are actually on the hyperbola. All right, so that's something to keep in mind there. All right, so we need to go out along that transverse axis, and that transverse axis is, if you extend it, would create a line. We don't actually extend it, we only just focus inside the rectangle. But if you kind of imagine it as a line that extends on forever, the transverse axis is just a line segment, but if it's part of that greater line, following that line would get you to your foci. All right, I need to go radical 5 away from the center, so that's somewhere between 2 and 3 units, so just plot it there and plot it right, yeah. So I'll call this one F1 and I'll call this one F2. All right, so we have our foci. Now in terms of the coordinates, well, I manipulated the center by adding and subtracting radical 5 to the x value. So my foci would be at the location of 1 plus or minus root 5, comma, what was it, 3. All right. So then the only thing that remains would be the equations of the asymptotes. Now that's actually very easy, and this also brings up a good opportunity for me to review writing the equation of a line, because there are many ways in which you can go about writing the equation of a line. The way, hopefully, your previous calculus teachers, if I happen to be that person, then you definitely got it from me. Hopefully the way that they told you was using the point-slope form, the equation of a line. If they did not, then, oh, here's something I should not be saying on something that's going out over the internet. I would be questioning their qualifications. All right, so it's y equals m times x minus x sub 1 plus y sub 1. All right, where x sub 1, no, you know what m is. X sub 1, y sub 1 is a point on the line. And it's one thing for an algebra teacher to focus on different ways to come up with the equation of a line, because they're trying to teach that skill for the first time. So they want to give different skills to different students. Maybe they want you to kind of explore it from different angles. But yeah, once you get to calculus, it should be point slope every day, all day. All right. Now, a point that's going to be on each of these asymptotes would be the center. That's a perfect opportunity. Now, all I would need would be the slope. So change of y over change in x, as you know. So we're going this away and we're going this away. So one slope, if I go up 2 over 1 to the right, would be 2. The other slope, up 2 over 1 to the left, negative 2. So my asymptotes would be the equations. Really, they're only differing by the slope, right? So it would be y, I'm going to thicken that up, y equals plus or minus 2 times x minus, we know the center is a point on the line, x minus 1 plus 3. All right. So I'm going to plot that, and we'll verify that those actually do at least appear to be the correct asymptotes. So y equals negative 2 times x minus 1. And you can simplify if you want, but the first step on the journey should be determining the equation in slope, point-slope form. So I would go ahead and, you see that little gear? If you're not familiar with Desmos, that little gear is going to be a good friend of yours. Tap on that, gives you the option to duplicate, and then hit done, and then you can just manipulate the new equation. I'm going to make that a positive instead of a negative. All right, and so you have essentially what you're looking for. All right, so then it's just a question of whether I typed in the original equation to begin with, and some of you must be screaming, or must have been screaming at the screen for a while now. You see here I typed in 4x squared minus 4y squared. I picked up on that only now because I see that it doesn't look like it's asymptotic. All right, so I knew that there was a problem, so I go fix that, and oh, look at that, that's picture perfect. All right, if I want to hit home to get the standard negative 10 to 10 window, I can move things around, I can pinch it out, pinch it in. I can get an estimate of where I think the vertices are just by kind of scrolling. If it's a nice clean number, then I can get those vertices. But in this case, it's kind of hard for Desmos to kind of lock in on it as a precise value. But eventually, it does get there. You just got to be a little patient. It will present you with intercepts, though, which is great. All right, if you just tap on those intercepts and any intersections between graphs, it'll always present that information to you too. So that's all good information. And so this video is a little bit longer, but as you can see, there's